Today we'll be looking at the derivative of logarithmic functions. Now, in the course of proving what the derivative of the natural log is, we will be relying on the limit definition of the number e. So we talked about this briefly in the chapter on precalculus review in our lecture on the number e. So just to refresh your memory, the number e can be defined as the limit as x goes to infinity of the quantity 1 plus 1 over x raised to the power x. So we show that this limit is this number e, and we motivated this in terms of compounded interest when we basically took the limit as the number of times where compounding interest goes to infinity. So if we compound interest continuously instead of at discrete moments in time, this number shows up, and this number can be defined as the limit as x goes to infinity of 1 plus 1 over x to the power x. So for this lecture, we'll take this as a given. Now, the function we're trying to differentiate today is just the natural log of x. So to do this, we start with the definition as we always do. So f prime of x is going to equal the limit as h goes to 0 of f of x plus h minus f of x over h. This is just the limit definition of the derivative. We take our function f of x, plug it into our limit definition of the derivative, and then take it from there. So we see what happens and we try to simplify it. And indeed it does simplify to something very nice. So replacing this with the function f of x is equal to ln of x, ln of x plus h, and then minus ln of x all over h. Now, this is a little bit different than, for example, when we took the derivative of a power function, in which case we could just expand the power, subtract off f of x, simplify things, and everything works out very nicely. But nevertheless, there is a practical way to simplify this and get the derivative as a nice simple function. And that is to use log rules. So we have ln of something minus ln of something. So recall that, so I'll just write the rule up here, ln of a minus ln of b is equal to the ln of a over b. So we'll use that rule to simplify the derivative as the limit as h goes to 0. I'll kick the 1 over h just outside, and we have ln of x plus h over x. So we have the limit as h goes to 0 of 1 over h times the ln of x plus h over x. Now, another log rule that we can use is a ln of b is equal to the ln of b to the a. Right? So this coefficient can be pulled up to the exponent of what's inside of the ln function. So we get the limit as h goes to 0 of x plus h over x to the power 1 over h. And this is the same as the limit as h goes to 0 of 1 plus h over x to the power 1 over h. Now right away I'm starting to see some similarities between what I have here. Of course I need ln. Don't want to forget the ln. So it's ln of this quantity. So it's the limit of the ln of this, limit of the ln of what we have right here. So this is starting to look, what's inside of the ln, very similar to what we have up here, 1 plus 1 over x to the power of x. So in that analog, let's continue and try to get this to even look closer to that. So if we have 1 plus 1 over x, here we have 1 plus h over x. So we can think that the x up here is related to x over h down here. And since we just have 1 over h, we can basically change that 1 over h in the exponent to x over xh. Right? 1 over h is the same as x over xh. So next I'm going to introduce a new variable. So I'm going to let y equal x over h. So if I do that, this becomes the limit. So if h is going to 0 and we have a fixed number x, x divided by h will be going to infinity, right? So if x is, let's just say, the number 1. When h is equal to 0.1, y will equal 10. When h is equal to 0.01, y will equal 100. When h is equal to 0.001, y will equal 1,000, and so forth. So in the limit as h goes to 0, y will be going to infinity. So when we swap h for y, we want to change this to the limit as y goes to infinity. And then we have the ln of 1 plus 1 over y. So x over h is just y, so we have y in the denominator here. And we have x over h up here, so that's just y over x. Now it's very similar to what we have up here, except up here we have an x and down here we have a y. So let's get this x completely taken out of the picture by using this rule up here one more time and rewrite this as the limit as y goes to infinity of 1 over x times the ln of 1 plus 1 over y to the power of y. Now x is fixed as we take this limit. So we can take this 1 over x and just pull it out. And also, I'm not going to justify this in great detail, but you can also basically move this limit into the ln. And so the limit as y goes to infinity of 1 plus 1 over y to the power of y is just equal to the number e. So what we have up here, when we take the limit as y goes to infinity, we just have 1 over x times the ln of e. And the ln of e is equal to 1, so we just get 1 over x. Next, we're going to see our extension of this rule. So we basically just showed that the derivative of ln of x is equal to 1 over x. So our extension will be the derivative of ln of u of x is equal to u prime of x divided by u of x. So this basically incorporates the chain rule automatically into the rule that we just proved. And again, we'll be talking about the chain rule in a subsequent section, but right now we'll just see how the rules work. So in other words, if y is equal to ln of u of x, we can write dy dx is equal to u prime of x over u of x. So whenever you have ln of something and you want to take the derivative, it's just the derivative of that something over the original something. So when you have ln of u of x, it's just the derivative over the original. So to see some examples of that, suppose we have y is equal to ln of 4x to the 4 plus 5x cubed plus 3x plus 17. So the derivative, dy dx, is just going to be the derivative of the inside over the inside. So we just get 16x cubed plus 15x squared plus 3 divided by 4x to the 4th plus 5x cubed plus 3x plus 17. Okay, this does look like 171, so let me make this absolute value sign a little bit larger so we don't get confused. Right, so what we did was we just took the derivative of this inside function and divided it by the original value. If we have y is equal to the ln of e to the 3x squared, say 3x squared plus pi, just to make it interesting, let's see what happens. Well, dy dx is just the derivative of the inside. Now the derivative of the inside, we have to go back to our exponential rule. So we rewrite the exponential, e to the 3x squared plus pi, and then we multiply by the derivative of the exponent, which is just 6x. And then we divide it by the original function, like that. And notice that the exponentials cancel out, and we just get 6x. Now that's reasonable, because if we simplified this expression, the ln of e to the 3x squared plus pi, It's just equal to 3x squared plus pi. So it makes sense that the derivative is just going to be 6x. Finally, let's look at one interesting example. Let's say y is equal to log of x. So this would be log base 10. Right? So usually when there's no base specified, you assume it's base 10. And then of course ln would be log base e. So what happens if we have log base 10? Well, it's not dy dx is equal to 1 over x. Not correct. So how do we find the answer? Well, we have to again rely on one of the log rules. So log base 10 of x is just equal to the ln of x divided by the ln of 10. You can try that. Log of 100 is going to equal 2, right? Because 10 to the power 2 is 100, so log of 100 is 2, right? 10 to the power 2 is equal to 100. Well, let's try the ln of 100 divided by the ln of 10. I think you'll find that the answer is 2 if you type that into your calculator. And we saw why this rule was true when we talked about logarithms in our pre-calculus review. So we can use this rule that log of x is equal to the ln of x over the ln of 10 in order to find the derivative of this log with another base. So if y is equal to log of x, we can rewrite that as just ln of x over ln of 10. Well, 1 over ln of 10 is just basically there's an invisible 1 right here, there always is. It's just our coefficient, so it's just like saying, well, if I have y is equal to a times f of x, dy dx is just going to equal a times f prime of x. Right? Constants are free to move in and out of the derivatives without affecting anything. So the derivative of this, the derivative of ln of x is just 1 over x, and then the coefficient 1 over ln of 10 just stays along for the ride. So the derivative of log of x is 1 over x ln of 10.